everyone, I am delighted to present our work titled EAS-SNN, End-to-End Adaptive Sampling and Representation for Event-Based Detection Using Recurrent Spiking Neural Networks. In this study, we introduce an adaptive sampling module that leverages recurrent convolutional SNNs enhanced with temporal memory, facilitating a fully end-to-end learnable framework for event-based sampling detection. Unlike conventional imaging sensors, event cameras, biologically inspired by vision systems, operate asynchronously, recording logarithmic intensity changes at the pixel level. These intensity changes, called events, enable event cameras to excel in unique areas: ultra-high temporal resolution, 10K fps, high dynamic range, greater than 120 dB, and extremely low power consumption, less than 10 milliwatts. These attributes make event cameras particularly well suited for object detection in challenging environments, such as those involving rapid motion, extreme lighting conditions, or strict energy constraints. Recent research has focused on utilizing the spatiotemporal characteristics of event data by refining aggregation functions and enhancing detection architectures. However, for event-based detection, a differentiable, adaptive sampling module that enables end-to-end optimization remains unfulfilled. Spiking neural networks, SNNs, comprising biologically inspired spiking neurons, present a potential solution for differentiable event-based sampling. First, SNNs support asynchronous event-driven computation on neuromorphic hardware, promising fast inference and low power consumption. This inherent compatibility with event data makes SNNs ideally suited for event-based vision tasks. Second, a spectrum of low-level representation methods can be encapsulated within a unified SNN layer. Third, the dynamics of SNNs align well with an ideal event sampler. When the accumulated, integrated information from the spatiotemporal event stream reaches a certain threshold, an event subset should be sampled, like spike firing in SNNs. Furthermore, this accumulation of information should be inversely proportional to the temporal interval of accumulation, like leaky current in SNNs. Motivated by this, we implement a novel adaptive sampling module that leverages recurrent convolutional SNNs with temporal memory, facilitating a fully end-to-end learnable framework for event-based detection. Specifically, our method employs pixel-wise spiking neurons in the sampling module to capture dynamic information from events across receptive fields. When the integrated information exceeds a predefined threshold, the events between the previous and current spike firing times are sampled. By optimizing spike firing times and membrane potential distribution, the sampling module can be trained and coordinated with downstream spike-based detectors, significantly reducing temporal misalignment between the raw event stream and SNNs. Our results indicate that an effective sampler must exhibit advanced temporal credit assignment capabilities to extract meaningful and discriminative substreams from noisy and fluctuating spatiotemporal event data. To this end, we incorporate a recurrent synaptic structure, as illustrated in the bottom left of the figure, to enhance the temporal representational capacity of the SNNs. After sampling, the challenge remains to effectively integrate each sampled event set into a coherent embedding. Our experiments show that decoupling the sampling and aggregation modules can lead to unstable gradient flow, hindering training. Thus, we unify these two components within a single SNN, using potential accumulation within the sampling window as input for the downstream network. This adaptive sampling approach allows for integration with the downstream detector for end-to-end training using backpropagation through time, BPTT, with surrogate gradients. However, the aggregation method implicitly optimizes the sampling module by relying solely on membrane potential accumulation, without accounting for the firing threshold, which is crucial for determining spike timing. To address this, we propose spike-aware training, SAT, which incorporates spike firing into the aggregation function and introduces threshold-driven gradient rewiring. This enhances the update of spike timings near the threshold, resulting in more precise sampling away from critical points. Additionally, we introduce residual potential dropout, RPD, to exclude events following the last spike, forcing the sampler to learn precise firing times. As shown in the figure, RPD leads to a more compact feature distribution, while SAT prevents mode collapse toward non-firing regions with concentrated negative membrane potentials. We validate our approach on the NCalTech 101, Gen 1, and 1MPX datasets. Ablation studies confirm that integrating components like the RSNN, sampling module, SAT, and RPD is critical for achieving optimal network performance. In Table 2, we compare our method with established event representations such as voxel grid, time surface, and voxel cube, demonstrating that our adaptive method outperforms these alternatives on multiple datasets. Furthermore, our framework can incorporate various event representations at early stages, further enhancing performance. Notably, the proposed adaptive sampling method extends beyond SNNs, showing promising results when validated on conventional non-spiking models. Additionally, our approach exhibits robustness, maintaining strong performance across various temporal granularities and sampling conditions. Finally, we compare our method with state-of-the-art spike-based models on the Gen 1, NCalTech 101, and 1MPX datasets, where it achieves superior results with significantly fewer parameters and time steps. For instance, on the Gen 1 dataset, our approach improves MAP by 4.4% while reducing parameters by 38% and utilizing only 3 time steps. It also demonstrates superior energy efficiency compared to traditional artificial neural networks, ANNs. Thank you for listening. If you have any questions, please visit Session 2 at Miko Milano on Tuesday, October 1st, from 16:30 to 18:30 or contact me by email.